So now that we have defined the integral, let's prove several of its properties. So as always, I recommend you to try to prove these properties before to look at the proof I will present. This will always allows you to understand where there is a difficulty. And here the problem is that one has to be very careful because there are certain properties which look obvious but which require proof because we define the integral through several steps, and so you need to check, go back to the definition in order to prove certain of these properties. So I'll start with two observations. The first one is, well, assume that we have a function f. So again, there is a certain measure space, omega, f, and mu. So assume that we have a function f, which is defined on omega, takes values in the extended line, and which is f measurable. So assume that f is integrable. And what I claim is that in this case, if I take any set A and I consider the function which is the indicator of the set A times the function f, so this new function, A here, it's always a set in the sigma algebra f, this new function is measurable and it's integrable. So to check that this function indicator of A times f is integrable, we have to take the positive part of this function and the negative part of this function and check whether these two non-negative functions have finite integral. So let's start with the positive part of this function. Well, the positive part of this function, it's clearly equal to the indicator of the set A times the positive part of the function f, which is bounded by f plus. So we didn't prove yet that if I have a non-negative function bounded by an integrable non-negative function, that this function is integrable. Right? We proved that at the level of simple functions, but here we are talking about non-negative measurable functions, so we need to prove that if I have a function g, which is non-negative, and a function f, which is non-negative, then the integral of g is less or equal than the integral of f. Well, how is the integral of g defined and the integral of f defined? Well, they are defined through increasing a sequence of increasing simple functions, non-negative simple functions. So let's denote it by Gn, a sequence of simple functions which increases to g. Let's consider the same thing as for f. So Fn, it's a sequence of non-negative simple functions which is increasing to f. And so we want to prove that the limit of the integral of Gn it's bounded by the limit. Well, that since we have no relation between Gn and Fn, there is no way we can prove such a thing. But what's clear is that f is larger than g. So if I take Hn and I define as the minimum between Gn and Fn, then this function here is clearly bounded by Fn. Gn it's increasing and Fn it's increasing, therefore the sequence Hn it's a sequence of increasing functions. Gn and Fn are simple functions, and the minimum, I leave that to you to check. If I take the minimum of two simple functions, it's a new simple function. So Hn, it's a sequence of simple functions. They are non-negative, and they increase. And what is the limit of Hn? Well, the limit of Hn will be the minimum between the limit of Gn and the limit of Fn. The limit of Gn is G, the one of Fn it's F, and the minimum between G and F it's G. So Hn, it's in fact an increasing, non-decreasing sequence of non-negative simple functions which is increasing to G. And therefore, I of G it's equal to the limit by definition, right? I have here a non-negative measurable function, a sequence of simple functions increasing to G. So I of G is the limit of I of Hn. But Hn, it's a simple function which is less than or equal to Fn, which is also a simple function. And we've seen that in this case, I of Hn, it's less than I of Fn. So this limit is less or equal than the limit of I of Fn, which is equal to I of F. Right? So we just proved that now if we have two non-negative measurable functions, one which is bounded by the other one, then the integrals are bounded. Right? Well, since we are proving certain properties of positive functions, let me mention another property of positive function, and then I will go back to the multiplication of an integrable function by the indicator of a set. So let's prove that if we have two non-negative functions, then the integral of f plus g, so here I'm assuming that f it's a non-negative measurable function, g it's a non-negative measurable function, and what I want to prove is that the integral of f plus g it's equal to the integral of f plus the integral of g. And if c it's a non-negative real number, then the integral of c times f it's equal to c times the integral of f. So we proved the linearity at the level of simple functions. I want to extend the linearity now to non-negative functions. And this is almost immediate. So we have to go back to the definitions. So let's take a sequence Fn of non-negative simple functions which increase to f. Another sequence of non-negative simple functions Gn which increase to G. So it's clear that Fn plus Gn it's a sequence of non-negative, simple because the sum of two simple functions it's still a simple function, so it's a sequence of non-negative simple functions which is increasing because both sequence Fn and Gn are increasing, and their limit is equal to f plus g. And for similar reasons, if I multiply Fn by a constant c times Fn, it's a new, since c it's non-negative, it's a new sequence of simple non-negative functions which is increasing to c times f. And therefore, just by definition, I of f plus g it's equal to the limit, right? Since I have here a sequence, it's by definition of the integral of a non-negative function, the limit in n of I of Fn plus Gn. Now Fn and Gn are non-negative simple functions, so I can use the linearity at this level of the integral but the sequence I of n converges to I of f because Fn is a sequence which converges to f, Gn is a sequence which converges to G, so this limit it's equal to I of f plus I of g, which proves the linearity. And now I can reproduce exactly the same argument to show the second identity. So with that, we just proved that well, the linearity property extends to non-negative measurable functions. So once we prove the linearity, we can give another proof of the monotonicity of the integral. Assume that you have two functions which are non-negative and such that one is bounded by the other one. So I can always write, in this case, f as g plus f minus g. So g and f minus g are both non-negative measurable functions. Then by the linearity for non-negative function which we just proved, we have that I of f is equal to I of g plus I of f minus g. We've seen that the integral of a non-negative function, it's always non-negative because the integral of a non-negative simple function, it's always non-negative. So maybe we didn't prove that, but let me just make a side observation here, is that if g it's positive, then I of g it's greater or equal than 0. And this just because, well, consider sequence gn increasing to g. Gn is formed, it's a sequence of non-negative simple functions. Then we know that I gn it's non-negative, and I of g it's the limit, so it's a limit of non-negative function, therefore it's non-negative. So this expression here, it's non-negative, and therefore we obtain that I of f it's larger or equal than I of g. So this is an alternative proof of the monotonicity of the integral at the level of non-negative functions by using the linearity. Now finally, let's go back to the indicator. So let me remind you what was my claim, and claim which forced me to go back to the proof of some properties of the integral restricted to non-negative functions. So I want to fix a function f which is integrable, a set A in the sigma algebra f, and my claim is that the indicator of A times f it's integrable. And so to prove that this function, and now I'm not assuming anymore that f it's non-negative, I'm taking any integrable function. To prove that this function is an integrable, I have to take its positive part and its negative part. So let's consider the positive part. The argument for the negative part, it's exactly the same. So let's consider the positive part of this function. Well, this is clearly equal to the indicator of A times the positive part of f. And this expression, it's bounded by the positive part of f. So this is a non-negative function which is bounded by f plus, but since f is integrable, the integral of f plus it's finite, and therefore by the bound we just proved, the integral of this function which is that function, it's finite. This proves that the positive part it's integrable. The same argument will show you that the negative part it's integrable, from which we will conclude that this function it's integrable. And so from now on, when instead of writing I of a function, I will instead write the integral of f d mu, which is the common symbol for the integral of f with respect to the measure mu. And instead of writing the indicator of A times f d mu, I will write that as the integral over a of f d mu. Right, so when writing this expression, what I mean is that I'm taking the integral of the function f multiplied by the indicator of a with respect to mu. But instead of writing this integral in this way, I will write it in that way, and we just proved that if f is integrable, then this expression makes sense. So a second observation, let's assume that f is non-negative and integrable, so that its integral it's finite. And let's consider set E, which whose measure it's equal to 0. Then I claim that the integral of f over the set E it's equal to 0. Right? Okay, so why this is true? So remember that the integral over the set AE of the function f, it's in fact the indicator of E times f d mu. Now, let's consider any sequence Gn of simple functions which increase to the indicator of E times Fn. Okay. So, since this sequence Gn is a sequence of simple functions, it increases to this function. This function vanishes outside E. So, it's clear that if x does not belong to E, Gn of x, which is smaller than the indicator of E times Fn, but since x doesn't belong to E, the indicator of E at x is 0, so Gn of x it's less or equal than 0, but Gn it's non-negative, so Gn has to be equal to 0 outside E. So I can, so this shows that Gn it's in fact equal to Gn times the indicator of E. Right? Because we just proved that outside E, Gn is equal to 0. So these identities hold if x does not belong to E, while if x belongs to E, this is trivial. But now if I compute the integral of Gn, so this is equal to the integral of Gn times the indicator of E, I claim that this is always equal to 0. Right? Why is that so? So let's, Gn, it's a simple non-negative function, so Gn can be written as a sum from k, which I did not use yet, from 1, say, to mn, of c and k times the indicator of some set f and k. If I multiply that by the indicator of E, what I'm doing here is taking the intersection of f and k with E, and therefore the integral of the indicator of E times Gn by definition is the sum in k of c and k times the measure of f and k intersection E. But by assumption, E has measure 0. So this set is contained in a set of measure 0, therefore the measure of this set is equal to 0. And so since c and k are real numbers, non-negative real numbers, 0 times this non-negative real number is 0, the sum is 0. Therefore, we just proved that the indicator of the integral of the indicator of E times Gn, which is equal to the integral of Gn, it's in fact 0. This is true for all n, and therefore this proves that the integral of f times the indicator phi is equal to 0. Here there is a mistake I just noted. I'm taking sequence g and converging to the indicator of e times f, not times fn, which doesn't make sense. Has not been introduced in this argument, right? So this argument I presented here shows that the integral of f times the indicator of the set E has to be equal to 0, which is what we claimed. So now let me start to prove some properties of the integral. So let's state a proposition. So we are working in some measurable space, and we have two functions, f and g, which are measurable and integrable, and two sets, A and B, which belong to the sigma algebra and whose intersection is empty, right? And so this is fixed, and I will prove several properties of the integral using these two functions and these two sets. Okay. So my first claim is that well, f plus g, it's integrable. Then well, c times f, it's integrable. We have seen that the indicator of a times f, it's integrable. And what I claim is that the integral of A union B of f, that this is equal to the integral of A d mu plus bf d mu. Okay. So before I start, I want to show that if two functions which are not necessarily non-negative are integrable, then the sum is integrable. If I multiply that by some real number c, then cf it's integrable, and that we have already seen, and that we have this property. So let me start with the first one. I want to show that f plus g is integrable. So I have to take the positive part of f plus g and the negative part, and show that the positive part and the negative part are integrable. Well, but it's clear that if you take two real numbers and if you take the positive part of the sum, this positive part it's bounded by the sum of the positive parts. And we have already seen that for non-negative functions, which is the case of f plus and g plus, the integral of the sum is equal to the sum of the integral. Since f and g are integrable, each of these functions is integrable, and therefore the sum is integrable, and this proves that this non-negative function, which is bounded by an integrable function, it's also integrable. So this proves that the positive part is integrable. The same argument will give you that the negative parts are integrable, and therefore that f plus g is integrable. So now let's prove that c times f, it's integrable. Well, if c is equal to 0, there is nothing to prove, because c times f it's the zero function, and the zero function is a simple function whose integral is equal to 0. So there is nothing to be proven. Then let me assume that c is strictly positive. Strictly positive. So I have to consider c times f plus, say. So c is positive, and I'm taking the positive part of c times f plus. So this is c times f plus. And again, this function it's now non-negative, and we have seen that the integral is linear for non-negative functions, so that the integral of c times f plus, it's c times the integral of f plus, which is finite because f is integrable, and we can exactly apply the same argument to the negative part. The negative part of c times f will be c times the negative part. So this is proven for c strictly positive. So now let's consider the final case in which c it's negative and the argument is similar, but now if I take the positive part of c times f plus, so I want this expression to be positive, but c is negative, so I have to take the negative part of c, so this is minus c times the negative part. So minus c now it's positive, and we can repeat all the arguments used before. So this shows that indeed if f it's integrable, then c times f it's integrable, and that one we have already seen. So last one is this integral. So let's write its definition. So I'm taking the integral of f on the set A union B. So by definition, this is the integral of A union B times f. And in order to prove that this function is integrable, I have to look at the positive and the negative parts of this function. So let's take the positive part. Well, but the positive part, since this is an indicator, is just equal to the indicator times the positive part. Now, since A and B are disjoint, the indicator of A union B is equal to the indicator of A plus the indicator of B. So this is equal to the indicator of A times F plus the indicator of B times F plus. F, it's integrable, so the integral of F plus, it's finite, and therefore that we have already proved, that if I multiply it by the indicator, we still have something which is integrable. The same thing holds for the second piece, and this shows that the positive part of this function, it's integrable. Same argument applies to the negative part, and moreover, so this is integrable. Now I proved that it's integrable. I want to prove now this identity. So to prove the identity, well, by definition, this integral, let me rewrite it here, it's equal to the integral of the positive part minus the integral of the negative part. Well, we proved that the positive part can be written in this way. So the integral of the positive part is the integral of this expression. These expressions are positive, so I can use linearity. So this is equal to the indicator of A times F plus the indicator of A times F minus d mu. Well, if I, instead of taking the positive part, I take the negative part, well, this is exactly the same. I have just to replace the positive part by the negative part in all these expressions. And so with this minus sign, what I get, that I have minus and here's B, I'm sorry, and here's the positive part, and now it's the negative part. Well, but now I can just, instead of taking A union B, take A, and observe that the positive part of the indicator of A times F, it's the indicator of A times F plus. So if we consider this difference, what I claim is that this is exactly equal to the integral of the indicator of A times F, because the positive part of this function is this one, the negative part is this one, therefore by definition the integral is equal to this difference. And in the same way, this difference is equal to the integral of f on the set B, and therefore if we recall that you started from here, that you arrived here, this is exactly our claim. So this proves the last of the observations I presented in this blackboard. Now I will prove a second property, so let me call that 2, is that if f is integrable, then f is finite almost surely. So remember that finite almost surely means that there exists a set E such that mu of E complement it's a 0, and that f is finite on the set E. So for any point on E, f is finite, or if you want, E is contained in the set of points in which f is finite, and here f is not necessarily positive, so I should write f instead of the absolute value of f instead of f. So let's try to prove. So my first claim is that the integral of f, the absolute value of f, it's an integrable function. So we've seen that the absolute value of f, it's a measurable function. Now what I claim is that, well, this non-negative function has a finite integral, and well, this is f, it's non-negative. F, the absolute value of f, it's equal to the positive part plus the negative part. Both of these functions have finite integral, which means that the absolute value of f has finite integral by the linearity of the integral for non-negative functions. So this is clear. Now let me consider the set of points which f is greater or equal to n. So this is a set, and let me integrate f over this set. Right? So on the one hand, this function, it's, so we have here a function multiplying by an indicator. So the function multiplying the indicator is smaller than the function, therefore the integral is smaller than the integral of f. So this is the inequality we have seen. If we have non-negative functions and one of them is smaller than the other, then the integral of one is smaller than the integral of the other. On the other hand, if you observe this function, well, I claim that this function is greater or equal than the function n times the indicator of the set in which f is larger or equal than n, right? Because on this set, f is larger or equal than n, so the absolute value of f is larger than n. So this function here is larger than that one. So if I take the integral, I get also this inequality. But this function here, it's a constant times an indicator, so it's a simple function, and the integral of this simple function, it's n times mu of the set F larger or equal than n. Okay. So we have just proved that the set of points in which f is larger or equal than n has measure which is smaller than 1 over n times the integral of f d mu. So this is an inequality which will be used several times. We just proved that the measure of the points for which the absolute value of f is larger than n, it's smaller than 1 over n times the integral of f. Well, but the points at which f is equal to infinity, so as these sets, and let me call this set an, it's a decreasing sequence of sets, right? I'm claiming that an contains an plus 1, right? Because if a point is in an plus 1, this means that the absolute value is larger than n plus 1, and therefore it's larger than n. So this sequence is decreasing. The intersection of an, so these are points for which f is larger than n for any n. So this is exactly the set at which f is equal to plus infinity. We proved that for any n, the measure of the set an is finite. Therefore, we can use the continuity from above to say that the measure of the points at which f is equal to plus infinity, it's the limit of these sets. So it's the limit on n of mu of f larger than n. And this limit is equal to 0 because as n tends to infinity, since as f is integrable, this expression is equal to 0. So this proves that the measure of the points at which f is equal to infinity is 0, which, so we can take this set as the set A complement. It's a measurable set because the function f it's measurable, so all these sets are measurable, belongs to the sigma algebra, and therefore the intersection belongs to the sigma algebra, so this set belongs to the sigma algebra. It has measure 0, and on the complement of E, which is the set E, this corresponds exactly to the set of points at which f is finite. So this proves our claim. So now let's prove that the integral it's linear. So I want to show that the integral of f plus g d mu it's equal to the integral of f d mu plus the integral of g d mu. For that, I will first prove the following fact. Assume that I have f and g functions which are positive, and I want to show that the integral of f minus g it's equal to the integral of f minus g. So let me call h the function f minus g. And here let me mention that when I write f plus g or f minus g, I'm assuming without saying it explicitly, but I'm always assuming that these expressions make sense. In the sense, remember that we are assuming that this function f and g takes value, they take value in the extended real line. So we could have that at certain point f of x is equal to plus infinity and g of x is equal to minus infinity, in which case this sum does not make sense. So when I'm writing f plus g, I'm always assuming that this is not the case, so that there are no x for which this sum is not well defined. And the same thing here when I'm writing f minus g, I'm assuming that there is no point in which f of x is equal to plus infinity and g of x is equal to plus infinity. So I'm assuming that these expressions are always well defined. So h, it's equal to f minus g. So let me call h the difference f minus g. So this, as I said, this function may take negative values, but it's always well defined. So we never have plus infinity minus plus infinity or minus infinity minus minus infinity. So let me take h plus. H can always be written as h plus minus h minus. So this function h is being written in two different ways, and it follows from the equality of these two expressions that f plus h minus, it's equal to g plus h plus. Right? So I claim that it follows from this expression that we have that one. So if these are real numbers, there is nothing to worry about. So we have to worry if one of them is plus infinity or minus infinity. So let's assume that h of x takes the value plus infinity. This means that f of x is plus infinity, and g of x, therefore, it's finite, right? Because I'm not allowing it to be, well, it could be minus infinity, but it couldn't be plus infinity. Since f of x is plus infinity, h is plus infinity, therefore h plus is plus infinity, and therefore h minus is 0. In this equation, we have, well, h minus is 0, f it's plus infinity, h plus it's plus infinity, and g, which is non-negative, cannot be take the value plus infinity, so it's a real number. So this is a real number, and therefore we have the inequality for, in the case in which hx is equal to plus infinity. And you can check that this expression, it's also well defined when h of x takes the value minus infinity. So let me repeat that just to make sure that I'm clear. By convention, whenever I write f plus g or f minus g, I'm assuming that this expression makes sense. So in this case, I have f minus g. F and g are non-negative functions. This means that I'm assuming that f does not take, and g does not take the value plus infinity at the same point. So h, it's well defined at all points. Now, if for any function h which is well defined, which has a value at any x, I can decompose it as its positive part and its negative part. Right? Now I claim that this equation holds. And for that, well, I just need to check if this holds. If these are real numbers, well, this identity follows from that one. I just have to be careful in the case in which h takes the value plus infinity and minus infinity to check if this inequality holds also in that case. So I'm taking a case in which h of x is equal to plus infinity, but if h of x is equal to plus infinity, this means that h plus is plus infinity and h minus is 0. Since g is negative, this means that if h is plus infinity, we must have that f is plus infinity, and therefore g cannot assume the value plus infinity. So since it's non-negative, it must assume a real number. And therefore, in this case, f it's plus infinity, g it's a real number, h minus, I'm sorry, it's 0, h plus is plus infinity. So let's check this identity. Well, we have indeed plus infinity plus 0, which is plus infinity, and on the other side we have a real number plus infinity, which is plus infinity. So it's indeed correct that this identity holds in that case, and we can check that it holds in the case in which h takes the value minus infinity. So now we have the advantage is now that we have two non-negative functions on the left-hand side and on the right-hand side, and they are equal. If we have two non-negative functions which are equal, it's easy to check that their integral is equal. And by linearity of the integral, f, well, the first term, it's equal to f d mu plus h minus d mu. And the second inequality is just g d mu plus h plus d mu. And therefore, since g and f are assumed to be integrable, h it's clearly integrable because h is bounded by the sum of f plus g, so h is integrable. So all these integrals are finite real numbers, so I can subtract and obtain from that f d mu minus g d mu, it's equal to the integral of h plus d mu minus h minus d mu. But this expression, it's precisely the integral of h. So we proved that the integral of h, that is the integral of f minus g, it's equal to the integral of f minus the integral of g, as I claimed. Right? So for any positive functions, the integral of a difference, it's equal to the difference of the integrals. With that in mind, we will prove this identity, the linearity. So f plus g, it's certainly equal to f plus. So f plus, it's f plus minus f minus. The same thing for g. So this is, so I can always express f plus g as f plus g plus minus f minus g minus. And since we are assuming that f plus g is well defined, you can check that these differences are well defined, right? So for instance, assume that f takes the value plus infinity. This means that g does not take the value plus infinity, minus infinity. So minus infinity is forbidden. So if minus infinity is forbidden, this means that g minus is a real number. Since f takes the value plus infinity, this means that f minus is 0. Therefore, this is well defined because f plus is plus infinity. Therefore, we have plus infinity minus a real number, which is plus infinity. And you can check with all the other cases that the right-hand side is well defined. If the right-hand side is well defined, I can use this identity. Here I have a positive function minus a positive function, so I can say that the integral of f plus g d mu, which is equal to the integral of f plus g plus minus f minus plus g minus d mu, that this expression, by the first statement I proved, it's equal to the integral of f plus g plus d mu minus the integral of f minus plus g minus d mu. Now, I will erase this line because I just used, I don't need it anymore. By the linearity which has already been proved for positive functions, this last integral is equal to the integral of f plus d mu plus the integral of g plus d mu minus the integral of f minus d mu minus the integral of g minus d mu. And we are done because we have here f plus minus f minus, which is the integral of f, plus g plus minus g minus, which is the integral of g. And this proves the third property, essentially one piece of the linearity of the integral for integrable functions.